Okay.
So, good morning, everyone. I welcome you all on the fourth day of short-term training program on Introduction to Seismic Analysis and Design of Structures. Today, Sir is going to deliver lecture on analysis and design of masonry infield RC frames. So, thank you, everyone, and now you may start, sir. I request all the participants to mute themselves.
So I can see someone has already asked a question
Yes, sir.
that for development of the response spectrum, design response spectrum given in the IS code, which type of ground motion is considered? So this is a design response spectrum. This is an average response spectrum, not developed considering one or two ground motions, but this is a result of thousands of ground motions for different types of earthquakes: deep earthquakes, shallow focus earthquakes, near source earthquakes, far source earthquakes. So there are a lot of ground motions that are there, and after that, this design earthquake motion, design response spectrum has been developed. You cannot develop it using a single ground motion. But there is an earthquake that is the 1952 Kern County earthquake, that is also called Taft earthquake. If you develop response spectrum 5% for 5% damping for this Taft earthquake, you will achieve a very similar response spectrum to what our IS 1893 has. So that is why you will find that in many studies people use this Taft ground motion earthquake.
Hello, sir. I have a question regarding yesterday's conversation.
Regarding?
Yesterday's conversation.
Yes.
Sir, you have said that we can reduce the live load in the design combination.
Yes.
So I have asked a few designers about this, and we had a discussion about this. So they said that in the 1984 code it was allowed, but in the recent 2016 code the clause has been dropped. So I also checked the commentary about this, and in it also they said that it is not allowed. So can you confirm about this?
Your voice dropped suddenly. You check the commentary and
In that also it was mentioned that we cannot reduce the live load. It has to be designed for full live load even in the earthquake combinations.
let me check it again, because as far as I remember, the reduction in the live load is still permissible. But I'll check again, and maybe in the tomorrow's presentation we'll discuss this.
Okay, sir, sure.
Okay. Okay, so let us start. So hope you can see the slides. So are the slides visible?
Yes, sir. Yes, sir.
Okay. All right. So this
Yes, sir.
this presentation is about how to analyze these masonry infield RC frames and how to design them. Design is very similar to what we usually do for other types of frames, but most important part here is how do we analyze it. Design methodology is more or less same. So we'll discuss some of the modeling techniques, and then we'll shortly, in brief, we'll discuss the design aspects also. So these are the masonry infield RC frames. You will find here that they have different shapes, different sizes, heights, and some are with beams, some are without beams, so flat slabs. The spans are different, the heights are different. So this is, and you will find different types of openings, partial height infill walls. So several types of masonry infill RC frames you can see. And if you remember the previous presentations, we also have a very vast variation. I mean, a very large variation in the material strength of masonry across the country. So with all these uncertainties related to material, related to configuration, the design and analysis of these RC frames with masonry infill walls becomes very complicated. So let us see how to simplify these effects. So there are primarily two components in the masonry infill RC frame system. One is the RC frame itself and other is the masonry infill. So when we add these two components, so we provide infill walls inside the RC frame. By filling the gap, we have this masonry infill RC frame system, which is basically, the primary idea of putting these walls as infill in RC frame is to create some enclosed spaces. But this was the idea when the masonry was used as infills long back, but then slowly we recognize that we can also use them in various other purposes. So not only in creating the enclosed spaces, but also for many other purposes. Now, because of that, several problems came up. If you look at the construction practice in some other countries, in some other developed countries, such problems are not there in those countries because these masonry walls are of course used in other countries also, but they are not used as infill walls. The lateral load, the lateral action of RC frame is kept separated from the lateral action of the masonry infills. So they don't interact with each other. Okay, so that means that masonry is not used as infill, but it is still used for creating the enclosed spaces. So that those kinds of structures are different type of structures. Here we are not talking about those structures which are in which the masonry walls are separated from the RC frame, but we are discussing those structures only in which there is an interaction between the infill wall, masonry wall, and the RC frame. So I think this slide we have already discussed that what is the role of infill and why do we use these masonry walls as infills. So we use them because it is very inexpensive material. It is available easily throughout India, across India, and it is not very expensive. So people use extensively. We treat them non-structural, obviously, because of various issues. First is related to the strength. It is a brittle material, right? The strength compared to reinforcement and concrete is less, but regardless of that, it is sufficient to change the response of the system, structural system. But then somehow we don't treat it as structural, primarily because it is a brittle material, and the strength varies from different failure modes. So here there will be several failure modes, and for those failure modes, it is not easy to determine the strength. You have to carry out large number of tests, which we discussed, I think, in the previous presentation. But anyway, we believe, we tend to believe that they will not modify the structural response, and that assumption actually make our life easier because we don't bother about masonry. But then during earthquakes, the story is different. These infill walls, they change the behavior of the system and change it considerably. Now, because of all these things, that it is very inexpensive, it is easily available, we don't bother about their structural strength, treating them as non-structural elements. We don't consider them important enough to, to consider their influence on the structural properties. So we don't consider them in the analysis and design. When I say we don't consider, we consider their mass, right? We consider the weight of these walls on the beams, but we don't consider their stiffness. So we don't consider their strength, right? But we consider their mass, because in our dead load calculations, all the loads will come, and this wall is actually imparting that load to the beam. So it is considered. But since we don't know how to consider the stiffness and the strength, it is not. We don't bother about it. So this is a variation of the compressive strength of individual brick units. This is not masonry, but individual brick units. The strength varies from 3 MPa to 30 MPa. In northern part of India, it is relatively higher. 30 MPa bricks are very commonly found. In southern part of India, getting even 5 MPa bricks is very difficult. And if you move toward western or northeastern part, we have average quality bricks. But then in uh, Manipur, the brick strength can go as high as 45 MPa, 40 to 45 MPa. So that is the huge variation, starting from 3 MPa to 40 MPa. It's a huge variation across the country. It's very difficult to actually have uh, developed some material model for these masonry, because it is not only about the strength, but all other properties of bricks, they are a function of strength. So it is actually difficult to guess or to estimate what will be the failure mode of these brick masonry walls for different strength of bricks, because it is not only bricks that are present in the wall, but also the mortar. So the interaction between bricks and mortar is quite complex, and the failure in these infill walls is actually depends on many parameters, including the relative strength of bricks and the mortar. Okay, but still we have to design. So we will see how do we do this. So this is how the masonry infill RC frame they behave during the when subjected to lateral loading. The frame is of course very flexible. When we apply the lateral load, the frame will try to deform in a flexural mode. When you insert this masonry wall as infill inside this frame, then this infill wall will not allow that free flexible movement of the movement of the frame. Now, because of that, what will happen? Some part of the frame will remain in contact with the masonry wall, and some part of the frame it will be detached. So there will be some gaps between the infill wall and the frame, and some part will be in contact. Now, this contact area between the RC frame and the masonry infill wall, it governs the load transfer path from frame to infill. So now you can realize that when the lateral load is, let us say, 0 here on the frame, then if you think that there is a perfect contact between the infill wall and the frame, then you are wrong. Because those of you who remember how do we construct this infill wall, first the frame is constructed, and after the frame is constructed, we start constructing this wall layer by layer by putting those brick courses. Okay, now it is not possible to fully remove that gap between the RC frame and the wall. So there will always be some gap, some micro gap will always be there between the frame and the wall. So you cannot say that there is a contact between wall and the frame. But when the vertical loads are applied, the gravity loads are there, when there is slight movement in the building, in that case you can say that now there is a proper connectivity between the wall and the frame. When the lateral loads act on this frame, in that case the frame starts deforming in a flexible manner, right? Infill wall is there, it will not allow that flexible deformation, so that full contact will develop. Now if you look here, the contact length between the frame and the wall is up to this point in the beam, and the contact length in the column is up to this point in the column. Similarly, there is a contact length here, and there is some contact length here, assuming that it's a multi-story building. Okay, so ultimately this part of the infill acts as a strut. Strut in the sense it is under compression. So when the load is from left to right, so the compression is along this diagonal. So the load transfer takes place from the frame to the infill to the another joint as a diagonal axial force in the wall. Now when you keep on increasing this lateral load, what happens that this contact length between the RC frame and the wall, it goes on reducing. But the force is also increasing. When you increase the lateral load, the amount of force that this infill wall has to carry will also increase. The frame will try to deform. Infill will not allow that deformation. So then the contact length goes on reducing, the gap goes on increasing. But the force also goes on increasing. Because of that, what will happen that the cracks will start forming in the infill wall. And we have already discussed why the cracks form in this direction. So for the load from left to right, the cracks will always follow that load path. That is because this part of the masonry is under compression, but the opposite diagonal is under tension. So when the tension is in this direction, the cracks will of course form in this direction. When we apply load in the reverse direction, because earthquake loading is always cyclic, so for that reverse direction, the cracks will also form in the reverse direction. So that is the reason that during earthquakes, if you visit any site or you see photographs of buildings with infill walls, you will always find these axe cracks in these infill walls. So this gives us some idea of the behavior of this infill wall in the RC frame. Now once we know this behavior, we can actually try to analyze, try to model them and try to design them. So the most important point that we can take from here is that the compressive strut action that develops in the infill walls under the action of lateral loads. Now here is the example of the multi-story frame. So if you have a bare frame in which there is no infill wall, you can see that the lateral loads which are acting on that bare frame, they are resisted by the formation of these flexural actions, by the bending movements. So primarily the frame action resists the load, the flexural action resists the load, the lateral loads. But as soon as you insert these infill walls in this frame, what happens that most of this lateral load is transferred through these infill walls as diagonal forces, as compression along the diagonal compression strut. Okay, so you can see here that the bending moments are not shown. So there is a reason why I have not shown the bending moments. It will be clear in the next few slides. But what is important here is that the primary action through which the lateral loads are being resisted is the truss action. It is not the frame action. So now the frame action has been transferred, has been converted into a truss action where most of the lateral loads are resisted by the diagonal compression struts. So there is a huge difference in the behavior of these two types of frames. But then we don't consider this change in the behavior when we design our buildings. Okay, we don't consider that infills play such an important role in the lateral force, in resisting the lateral forces. So just to show you what happens in real life, do we really get these axe cracks? Do we really have that strut formation? I'm showing you a video of a frame with infill wall that was tested in laboratory, in our laboratory here at IIT Guwahati, and just try to see what type of cracks uh, uh, are formed in the beginning. Okay, and then what type of cracks will form towards the uh, are formed in the RC members towards the end of the test. Okay, finally you will look at how the failure has taken place. So 3-4 points are very important. Just have a look at this test. We have increased the frame rate here so that the test, this video will be complete within I think 30-40 seconds, but the actual test required about 2.5 hours, 3 hours to complete because it is a slow cyclic test. So if you remember yesterday's presentation, how do we design the structures? How do we apply the lateral loads? From the base shear, we distributed to different slab levels. Why slab levels? Because masses are concentrated on these slab levels. So here also you will find that the lateral load is applied at the slab level. So this is not the shake table test, but this is a quasi-static cyclic test. Loads are applied at the slab level using servo-controlled hydraulic actuators. So let us see, and the box, you can see central box at the bottom, that will give you, that will show you how much deformation we have applied at the top of the slab, at the top of the frame. This is a deformation controlled loading. Remember why deformation controlled? Because you want to record what happens after reaching the peak. So let's start the video. So you can see here that about 10 mm displacement is reached at the top, and I hope you can see the X cracks in the wall. So there are X cracks along the diagonals, and you can now see there are several cracks in the columns. We have reached about 35 mm displacement at the top, and you can very easily see the shear cracks in the columns. And now you can see the cracks distributed to all parts of the infill walls. Cracks, and now the failure has started in the column. So the right bottom column is failed. And after that, you see what happens to the infill wall. It is now falling in the out of plane direction. On the wall, on the bricks, they fell in the out of plane direction. Okay, so just remember what happened. Initially, if I again start this, initially the cracks were at the middle bottom half of the masonry infills, but slowly you could trace the X diagonal cracks in the frame in the infill wall. That is because the loads are applied in the cyclic manner. And once the diagonal cracks forms, X cracks, then you will find that these cracks, they are transferred, they are carried over to the RC frame. Inside they are continued to the RC columns. And these cracks, they are finally responsible for the shear failure of these columns. Sorry? And the final failure of this is by the shear failure of the columns and out of plane failure of the infill walls. Right? Initially, the failure started in the in-plane mode, but you will find that the failure. Here you can see small cracks at the middle half, right? And now you can see the diagonal cracks very easily visible from the top right as well as top left, and at both similarly both diagonals at the bottom. Right now you can see the cracks continued into the columns. In both the columns, both at top and bottom. And you can see there is a separation between the infill wall and the column. Now I will stop this test here. Maybe let me show what I wanted to discuss once. Yes, maybe here. So, can you locate the location of the column where maximum damage has taken place here? See, the maximum damage has taken place in this region, then this region of the column. There's some damage here in this region and some damage is here. But then there are cracks along the length of the column, but not major damage, right? So if you remember, you see that the failure has started here. There's a major damage here in this region and in this region. So this is the same thing that I have been talking about in the last 2-3 days, that these are the regions where you have huge rotation demand. There's a huge bending moment. So because of that, the failure, the hinges, the plastic hinges, they form in this region. But then these plastic hinges did not form when the masonry was resisting the load up to this point. Right? Because most of the load up to this point was actually resisted by masonry as the diagonal force, as the diagonal compression strut. But as soon as the masonry starts failing or it starts reducing its capacity, then the load is transferred to the RC frame. Right? So up to this point it was okay that masonry was actually able to resist all the load. But once it starts failing, or once some of its brick members, some of the bricks they crushed, then the entire load is transferred to the RC frame. Now this is most important part in design of infilled RC frames, because even though you have infill walls that resist the initial load, but what will happen if these infill walls fail? In that case, the entire load is transferred to the RC frame. And if you don't design these RC frames for this kind of load, you will have such kind of failure. So now you can see both the plastic hinges formed here, they failed, and the wall collapsed in the out of plane direction. So let us move forward. Let us see what are the failure modes. So some of these failure modes were visible in this video. First is of course the frame infill separation. Now this is not a real failure mode because like I said, there is always a gap, there is always a separation between the frame and the infill, even before application of any load, because it is not possible to actually fill all the gaps using the construction methodology that we follow. It's a different issue if we somehow use some pressurized cement grout and then try to fill that gap. It reduces that gap, but still 100% reduction is not possible. But then what will happen if there is a frame infill separation on all the sides? In that case, the wall will simply fail in the out of plane direction in the other side. If you remember the first presentation in which I showed you some failure in the real earthquakes, that is what happened. So the whole wall was still, you could have seen the whole wall tilted in the out of plane direction because the frame infill interaction was lost. It was totally, frame and infill was totally separated. So that whole wall fell in the out of plane direction. So this is a passive type of failure, not the active. Then the diagonal cracking that you have already seen, that when you apply the load is transferred through these infill walls as the diagonal compression strut action, and you get these cracks. Bed joint sliding, you could have seen the horizontal cracks in the infill walls along some certain bed joint. So, but then here it was a mixed mode of failure. You had diagonal cracking, you had frame infill separation, you also had bed joint sliding. But in some cases, you will only get this bed joint sliding. Those are the cases in which the mortar strength is very low. So mortar is very weak and the bricks are strong. So what will happen? The mortar will fail suddenly, very quickly. Then you have the corner crushing. You have seen how the bricks at those corners crushed before the RC frame failed. Finally, the shear failure of column. You have again seen this kind of failure, and the out of plane collapse. So that usually occurs in the end if you have a good contact, good interaction between the frame and the infill wall. But it can happen early if the interaction is not good. So that is what all these types of failures we have seen actually in the real testing. But the interesting point is these failures do not occur as individual failures. We always see a combination of all these failures. So if someone asks you to design a frame for diagonal cracking only, it's not right way to design it because it depends on many other parameters, many other factors on which the final failure mode depends. So we have to actually design for all possible failure modes, considering everything. Now, we can actually design uh, these walls for in-plane action, but then for out-of-plane action, it is difficult to design because there is nothing that is stopping these walls from failing in the out-of-plane direction. So maybe initially we could develop a very good interaction between the frame and the wall, but with the increasing lateral load, we can always have that interaction lost. We can always have that separation between the wall and the frame. So if that separation occurs, obviously this wall will fail in the out of plane direction. So we cannot design these walls simply by increasing the forces or by doing something in the design aspect. So what we do to avoid the out of plane failure, we try to integrate these infills with the frame using various methods. So we try to prevent these out of plane failures rather than designing these walls and frame for the out of plane failure. Now, what are the ways to prevent the out of plane failure? There are many ways. For example, we have to check the slenderness of the infill panels. So what we observe that the long walls, for example, the walls in the classrooms or in hospitals which have longer rooms, so those walls are more susceptible to out of plane failure. Now, simply because they vibrate in the out of plane direction and the mass is large. If the height of the wall is more, in that case what will happen? You have that bending action in the wall. But if the length is large, then you simply have that out of plane failure. The whole wall tries to move out. So we can provide some reinforcement bars, or we can provide some FRP sheets or strips like is shown here. So these are some FRP sheets or some reinforcement bars that we can provide on the faces of the walls by connecting them to the RC frame. So this is one way, and then we can plaster this thing so that this is not visible. Another option is to integrate the wall and the top beam and of course the column by using these metal angles. So we can have one metal angle here, another here, maybe another here. So distributed maybe at a spacing of 0.5 meters or 1 meter, or depending on the length of the wall and depending on the thickness of the wall. So these metal angles can prevent the out of plane failure of these walls. Okay, and these are small angles. So if you can see, I mean, imagine that is a stability problem. Out of plane is a stability problem. So even if you have very small minor arrangement to prevent this out of plane loading, you can actually succeed in that. So this is another method. Third method, which many countries follow, because these types of structures, they look very nice, very good. So it is a tongue and groove arrangement. So they create in concrete such an arrangement where infill wall can go inside. Now it cannot be done on both the faces, right? It has to be done on one face, and on another face you may provide the metal angles. Then metal dowel grouted into hollow brick. So this is another possibility that people do. So these bricks, maybe at intermediate levels, you can leave some gap, maybe of half brick length or full brick length, and you can have this metal that goes into that gap here in the brick wall, and it is drilled inside the column. So this is what people do. Then the flat metal strap nailed in perpendicular. So another, I mean, similar like this. So we have, instead of the metal angles, we can have the steel flats, which are inserted into the wall, and then one part is actually anchored to the columns or the beams. So there are different methods people follow in trying to prevent the out of plane collapse. Now let us come back to the in-plane behavior. So in-plane behavior, we have to uh, model these walls as infills and then try to see how they behave. What is the influence of these infill walls on the columns and the beams, and then try to design them so as to prevent the shear failure in the columns and possible failures in the beams. Now, one interesting point here is during this entire testing sequence, and I have just shown you one frame. We tested, I think, more than 25-30 frames, but then we have never found significant damage to beams of any of these frames. That is because of the slab action, that is a T-beam action. The beams are really stiffened in these cases. So most of the damage is actually concentrated in the RC columns. So we have to worry more about the columns rather than worrying about the beams. Of course, the minimum design should be there for the beams, but columns are more susceptible for damage here. And reason is very simple. I'll show you why. So modeling approach is obviously, like you have seen, there are two possibilities. One possibility is using simplified models in simple structural analysis package like SAT 2000 or STAT. This is very simple. So we can use different types of models. For example, equivalent diagonal strut model, or even a shell element model if you are doing a linear analysis. This is one possibility. Another possibility is you use some finite element software like Abacus or ANSYS and try to model this infill wall, maybe as a single unit or maybe brick by brick, and try to model the interaction between different bricks, different mortar, and the RC frame. But this finite element modeling, which is called the micro element modeling, it is not possible for a big building. Maybe one or two walls you can model, but not the entire building. So people do the macro element modeling. They don't model brick by brick, But then they model the entire infill wall as a continuum, as a single element, but they discretize it into several small elements, and then the interaction between the frame and the infill wall is modeled. The individual discretized elements in the macro element modeling is also provided with the tensile strength and the compressive strength and also the shear strength of the brick. But still, that is also complicated. We cannot again use it for big buildings. So I will not go into those details, the finite element modeling. I will discuss only about the simplified modeling of these infill walls. Primarily, that can be done in SAP 2000 or STAD kind of software. Only for building frame analysis, not for the finite element uh, research analysis, finite element analysis for research. So, like we discussed, we have this masonry infilled frame, and we go on increasing the lateral load on this frame, we will see that this gap will increase. So the amount of, or the area of the wall that is in contact with the RC frame goes on reducing when we increase the lateral load. Okay, but important point is the axial force increases. Though the area reduces, the axial force goes on increasing. So this behavior, this typical behavior of masonry infill RC frame gave rise to this simplified modeling techniques, that we can model this as a single element here. Because if we can model this column as a single element, the column is also having some dimensions, right? Some width, some depth. The beam is also having some width and depth. But we can model these beams and columns using these line elements, using the frame elements. Similarly, though it also has some finite dimension, this strut, we are modeling it using a single frame element, which is very similar to these beams and columns. But there is a difference. So we can model it using a single strut, but then people have actually tried to model it using multiple struts. So I'm showing you just 3 struts here. People have tried even 11 struts. And why? Because when you analyze this type of building, this type of a frame, by modeling the entire wall as a, let us say, shell element, in which the entire shell elements are connected to the entire frame. So you can imagine that such a system will always give you higher stiffness compared to this system, in which there are some gap areas. And this stiffness and strength here will further reduce. The stiffness will further reduce. So, second point is, let us say that the lateral load increases up to this level, and this strut is having this size. This is the finite size of that strut. So what will happen when the lateral load is transferred to the strut as diagonal action force in the wall? There is always a tendency for the column to exhibit some large force here, shear force here, because this part of the strut, this part of the wall is under tremendous axial load. So it has to actually transfer that load. So some part of that load, when this lateral load is applied, is actually transferred to the column here. So uh, this beam, this column may not be designed for that load. So that is why you will find that some type of damage may occur to the column. In this case, when you have the contact area further reduced, the damage will be here and damage will be more in this region, right? The reason is the axial force has increased. Though the area has reduced, the force has increased. So the point is, can we model this damage to the column, the failure that may occur in this column using single diagonal strut? The answer is no. We cannot model that type of failure, that type of damage to the columns using single diagonal strut. So therefore people thought that let us model multiple struts then. So in addition to this diagonal strut that connects the two beam column joints, they also model these two additional struts. Now this strut will directly transfer that axial load to the column, and you will have some damage to the column here. Similarly, you have some damage to the column. But then the question is, then why not we consider damage here? So that gave rise to multiple diagonal strut model. People have actually tried 7 strut, 11 strut model. So what happens then when you go on increasing the lateral force? These struts, they go on failing one by one, right? So for smaller lateral force, all the struts will be activated. When you go on increasing the lateral force, one by one, these struts will fail, and the activation of only limited number of struts will be there. So like this. But then this also did not solve the problem, because here what will happen that the entire shear force is transferred at a point, right? Here what was happening? The entire force from this strut was actually transferred to this length of the column. So the failure was gradual here, but in this case the failure was sudden because the entire force was transferred to a point. So that is why people were not really happy with even the multiple strut models. So therefore, it is not very common. Still, people still do that, but only the even the single diagonal strut model will solve our purpose. If we are not worried about what is a failure mode in the column, if we are only worried about the overall lateral strength and stiffness of the frame, overall design, then this is okay. Single diagonal struts are okay. Now, one important point here is you can see these circles here. See at the ends of the diagonal strut, you have these circles. Now, these circles are the uh, additional moment releases that are defined when you model this strut. Now, what are these moment releases? It is like a hinge. So, when you try to apply the lateral load from the frame and on the frame, and this frame transfer this lateral load to the infill wall, the load is transferred as axial force, but the flexural action is not transferred. The reason is the masonry cannot take that bending load. It is very weak in tension, so flexural loads masonry cannot take. So in order to avoid that transfer of that flexural action from the frame to the wall, these hinges are defined here. So whatever flexural action is here, that will not be transferred to the masonry here, that is the strut. So we define these moment releases at both the ends, here as well as here. So there is a way in the software that you can actually define these moment releases. So this I think we already discussed that what happened when we model this infill walls using different techniques. So here what I am showing you is the force resultants in the columns. So the bending moment, shear force and the action force in the columns when we model these infill walls using variety of techniques. So here the infill wall is not modeled. So you can find that the bare frame has large amount of bending moment and shear force. Of course, the axial force is there. So these are the bending moments and the shear force and the axial force because of application of the lateral loads. When we model the infill wall as this shell element, the entire wall is modeled here, then you can see that the bending moment is reduced drastically from here about 80 to maybe about 5 to 10, right? So reduced by about 10 to 12 times. Similarly, the shear force, it reduces to about 3 times. Axial force, more or less, it remains same in the columns, slight reduction. Now, if you model the infill wall using a single diagonal strut, then you have still reduction in the bending moment, but not as large reduction as this. Okay, so but reduction is still there, even in shear force and axial force. So axial force reduction is much more in case of columns, because now the entire load is resisted by the single member here. But in this case, the entire load was resisted by the entire wall. Okay, so that is the reason I was telling you that people tried this multiple strut model. So if you use this multiple strut model, you will find that axial force again increases in the column, but the shear force and bending moment also increased. Okay, so this is difference. This is a different behavior compared to the shell element. Now, if I model reduce shell elements, so I removed some of these shell elements from here and from here. I again get a similar response, right? So the question is which model you will prefer in among all these. So it depends on what type of analysis you would like to do, because in all cases the bending moment reduced drastically. So you can use any of these models. The shear force reduced in these two models, but other models there is an increase. So let us say you want to carry out a nonlinear analysis. Then you don't have a choice, much choice here. You have to use these elements. You cannot use the shell element in these types of models because the nonlinearity cannot be defined for infill walls in shell elements. In at least SAP 2000, I can tell you. Even in STAD, if I'm right. But if you are using Abacus, then of course you can model the nonlinearity in entire brick elements of the shell elements. So if you are doing nonlinear analysis, we always use the single diagonal strut or the multiple diagonal strut because it is easier to model the nonlinearity in these frame elements. Okay, so this is the section of the column that the analysis was done. Similarly, this is the analysis of the beams, and you can see similar results here. So if you model the entire wall using this shell, you have drastic reduction in the bending moment. But using these diagonal struts and these reduced shell models, you have again half 50% reduction, but then compared to shell, it is still more. And it is truly applicable, equally applicable to shear force and axial force also. And just see what happens to the axial force for the diagonal strut, single diagonal strut. It reduced drastically. Again, because only one element takes the load, transfer the entire load. Okay, so similar conclusions can be obtained from here. So again, any of these models is equally good, but because of the simplicity, most of the people use single diagonal strut because it does not have much advantage. It cannot predict the shear forces accurately. It can predict, but not that accurate. All right. So assuming that now we have some confidence over the equivalent diagonal strut modeling, and we know why do we model the infill wall using this modeling technique. Let us try and see how do we consider different parameters. So what is the role of this diagonal strut? First role is to impart the realistic stiffness to the frame, because we know when the infill wall is provided, it increases the stiffness. The second thing that it does, it increases the lateral strength. So we have to model the strength of the infill wall. We have to model the stiffness of the infill wall, the strength of the infill wall, and what is remaining? Now only these two, but the mass we have already been considering. So the mass will always be there. Now how do we consider the strength and stiffness? So let us see how do we model the stiffness first. Now you know that the action here is the axial deformation in the strut. So what is the axial stiffness? It is simply AE by L, right? So there are three parameters here. One is A, which is the cross-sectional area, not of the wall, but now of the equivalent diagonal strut, right? So the diagonal strut should have sufficient cross-sectional area. Now the strut has a rectangular or a section which is very similar to the column or beam. So it's a rectangular section. Okay. Next is E. So the modulus of elasticity of this diagonal strut, which comes from the material. So it's a modulus of elasticity of masonry. And third component is L. So it controls the slenderness. It is the total length of the diagonal. Right. So E, A and L. So E comes from material, A and L comes from the geometry. Okay, so two parts are involved here. We have to model both. Now, when I say that this diagonal strut has, let us say, a rectangular section, so that rectangular section will have depth and it will also have some width. So, width of this rectangular section of this diagonal strut is shown here. This is WDS, so width of the diagonal strut. This is the width of the strut. The depth of the strut is in the perpendicular direction, so it is along the depth of the screen. Now, obviously, the depth will be equal to the depth of the wall or the thickness of the wall, right? And how much is the width? That depends on many parameters. So it depends on the relative strength of the frame and the wall. It depends on relative stiffness of the frame and wall. It depends on the slenderness of the wall. It depends on the diagonal length. It depends on many parameters. So I'll show you some equations on how to calculate this width. But remember, the depth of this diagonal strut is equal to the thickness of the wall. So that is what is shown here. So this is one dimension of the strut. The other dimension, which is the width of the strut, the most simplest thing is to consider this width as 1/3 of the diagonal length to 1/5 of the diagonal length. That is what is the experience. Since last maybe 70 years of research on infilled RC frames, we have found that this width varies from d by 3 to d by 5 to d by 6. Now d is not the depth of the strut, but d is the diagonal length of the strut. Okay, so this d divided by 3 to 5. That is WDS. And what is the modulus of elasticity of the diagonal strut? It is the modulus of elasticity of the masonry. Okay, so that is how we define the material, we define the cross-sectional area. So what is unknown here? We know the thickness of the wall already, so one dimension is known. We know this diagonal length also because we know the dimensions of the frame. So this we can find out. So we know how much is the cross-sectional area of the strut. If we know what is the modulus of elasticity of masonry, we can model this AE by L very easily. So stiffness is taken care of. We can do this. So those of you who know how to model the RC frame only, they will be very easily able to model this diagonal strut also. It is exactly similar. The only difference is you need to create this additional hinges here so that the moment deflection is not transferred from the frame to the wall. Now, I think we already discussed that this modulus of elasticity is about 550 times the compressive strength of masonry prism. Okay, what is this masonry prism? Masonry prism is the same prism that, if you remember, that person was actually breaking a series, some height of the this masonry wall, right? So several bricks were there. So if you want to test this masonry prism in lab, the method is you consider 5 bricks one above the other, and there is a mortar joint in between. You test it just like you test the concrete cubes. So you cure it for 28 days because there is a mortar, and after 28 days you test it in the compression testing machine. You will get this FM. We define it as compressive strength of masonry prisms. So you multiply this Fm with 550, you get the modulus of elasticity of masonry. So that is the first part coming from material. Geometry, we already seen the width of the diagonal strut is 1/3 length of the solid infill wall. We will discuss what happens when there are openings in the walls. The calculations become slightly more complicated but still manageable. Now, you can imagine that if there are openings, obviously the contribution of the infill on the overall lateral load capacity will reduce. The stiffness will reduce. The strength will reduce because of presence of opening. So obviously the width of the diagonal strut has to be reduced, because if you consider AE by L, that is the stiffness. That means if you want to reduce the stiffness, either you have to reduce A or E, but E, the material part, remains the same. So you have to reduce the A. In A, you have the thickness of the wall which cannot be reduced. The only thing that can be reduced is the width of the diagonal strut. So that will be even less than 1/3 then. Thickness of the diagonal is the actual thickness of the wall. And finally, the important point here is the ends of the diagonal strut. So these are the 4 important points that you have to remember whenever you want to model the stiffness of the wall, right? So ends of the diagonal struts have to be pin jointed so that no moment transfer from RC frame to struts. Now let us worry about the strength of these masonry infill wall. How do we model the strength? Stiffness we have modeled. Now this strength comes from the, so as soon as we say strength, it has to be coming from some code, because there are various failure modes as we have seen. So strength should correspond to a particular failure mode, right? Because we cannot say that this is masonry and this is the strength. We can say that this is masonry and this is the compressive strength of masonry prism. Like we say that this is a concrete column, but this is the characteristic strength of cube strength, like the characteristic strength of concrete cube. We cannot say that this is the strength of the column, because when we talk about material, it is the concrete cube. Similarly, in masonry, we can say that this is the compressive strength of masonry prisms. But then when we talk about strength of infill wall, we have to specify what type of failure we are talking about. For example, we have to specify this is the compression capacity of the wall, or this is the sliding failure capacity of the wall, or this is the tensile strength of the wall. So many failure patterns are considered. But we assume that there is no tension in the wall, as long as we are considering the linear static analysis, linear analysis. So let us see, before we actually go to these codes. For example, like I said, you have to check this Indian code for finding out the strength. So Indian code is IS 1905 as far as masonry is concerned. So that will tell us about the strength. You should not start looking at the strength of the masonry in IS 1893, because 1893 gives you the design forces. It does not tell you what is the capacity of the building. It only tells you the design force. So we'll come back to this later, but let us worry about first what is the influence of openings. They have huge impact, huge influence on the lateral strength as well as stiffness. So when you go on increasing the opening size, you go on reducing the lateral stiffness, obviously, because the material that resists the load will go on reducing. So when the material, there is less material to resist the load, obviously the stiffness will reduce, the strength will reduce. Now the question is, how do we consider it? So the obvious way of considering the influence of openings is by reducing the area of the strut. That is the most obvious way, rather than worrying about anything else. So people have done some research. For example, this research on central openings carried out in 2008, they proposed that the equivalent diagonal strut, the reduction in the width will be given by this factor, rho w, which is 1 minus 2.6 times AR. So area is the opening, AR is the opening area ratio. Now what is opening area ratio? It is a ratio of opening area to the area of the infill. Okay. So what they say, that you compute this factor using this equation and then you reduce this WDS. So this factor will always be less than 1, obviously. So this WDS will reduce. So we call, if there is an opening, we call WDS as WDO. It's a factor of WDS, right? It may reduce by 20%, 30%, 50%, depending on AR, the opening area ratio. So their study was applicable, it was an analytical study, it was applicable for the opening size between 0.05, or the AR between 0.05 and 0.4. So this is one major study that was carried out. Later, people have actually carried out a lot of studies. So one interesting study was carried out by a student here in IIT Guwahati. It was published in a paper in 2020. So the study was really interesting. Here you can see that the x-axis, you have again the area opening ratio, right? On the y-axis, you have stiffness reduction factor, and on the another y-axis, you have strength reduction factor. So now this study gave you different factors so that you can reduce the stiffness and you can reduce the strength. Okay. So this is the factor Rk for the stiffness reduction, which is 1 minus Ar to the power 0.55, and to reduce the stiffness you have 1 minus Ar to the power 0.65. So again, this study was also applicable for opening area ratio of less than or equal to 0.5. Now this AR of 0.5, so 50% opening area ratio is very high. So you can imagine how big that opening will be if you have 50% opening. So you have very small amount of masonry wall there as in fill. Most of the wall will be opening. There will be no material there. So this study actually carried out some experimental tests as well as they compared the results with the past test. You can see here that these marks, they show the experimental studies, the pointers, and this line, it is actually the predicted result using these equations. So they match very well, both the stiffness and the strength. So the interesting feature here is it gives you the reduction factor that you have to apply to the strut if you want to reduce the stiffness or if you want to reduce the strength. So in other words, it will give you these factors so you can directly check the reduction in the stiffness or the strength. So this is one step ahead of this method that only gives you the effective width of the strut. Now, then there was
Sir,
another study. Hello.
sir, I have a question.
Yes.
Yeah, sir. Actually, in the last slide, can you go please on that slide? Yeah, in this slide, actually, in experimental results, whatever you are showing here.
Hmm.
So in lab, if we do the experiment, and for that, if we do the casting, so it is quite means quality control is better, and all those things are much better as compared to
Yes.
on field. So
Yes.
do we need to consider that factor, or does it have been already taken into consideration in this expression?
Yes. Very good question. See what happens in lab settings. We consider that this is the best we can achieve,
Yes, sir.
right? We cannot have a better result than this.
Yes,
Better
sir.
material, better quality control, better construction, better labor, better supervision. So
Yeah.
this is the best we can achieve in the country in laboratory setup, right? Now this is very interesting because then we can say when you go on site, you cannot even achieve this.
Yes, sir.
So nobody can claim that on site I will do better. So I'll reduce these factors,
Okay.
right? So this is the best you can do.
Okay.
These are the upper limits. So that is why we always are very happy with this lab setup because we
Okay.
know the upper limit of the things,
Yeah.
right?
Yes. Okay, sir.
Okay. But having said that, in lab also, we don't ask the masons or the laborers to actually do as per my wish. We
Yeah.
ask them, you try to be as realistic as possible, as if you are working on a site. So
Hmm.
you try to be doing that, but if he's doing something incorrectly, then we'll ask them that this is not the correct way. But then we
Okay.
don't interfere much. We tell them the quality control is up to us, but then we ask them to be realistically, to do the work realistically.
Yes.
So, so both these studies were actually carried out on central openings. This one, Mandal and Jain and Basha et al. So it was carried out on central openings. But then the openings can lie anywhere in the frame. So then how to handle them? So one student here, IIT Guwahati, he carried out a study in 2012, again analytical study. So he considered the influence of this opening anywhere on the frame, and then he developed this equation using which we can actually estimate the normalized width of equivalent diagonal strut, normalized to the uh, width of strut considering no opening, right? So this is again the reduced fraction of that no opening width. So it depends on Q and R. So these are the Q and R values. So R is of course the opening area ratio, and Q is the shortest distance between the center of the opening and the diagonal. Okay, so this Q is the distance. So you can move this opening anywhere, it can be anywhere, and the size of the opening can also be anything. So both are incorporated here, and this equation will give you that reduced width of strut. So many such studies are available in literature that tells us what is the reduction in the strength and stiffness. So that is one important aspect. Another important aspect in analysis and design is how to take care of these short column effects that are there because of construction of only uh, 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 the wall only up to a limited height. So if you remember the first presentation, the problem of having these discontinuous or construction of walls only up to a limited height is that some part of the column is not supported laterally, right? Like here, there is opening here, but some part of the column is supported. So if you look at this figure here, this is a long column, right? But let us say we have wall up to this length, this height of the column. So then this free length of the column becomes very less. For example, this column here, right? So it becomes a short column. Now what happens that this long column, if you remember, what is the shear? The M by L, right? So L is long, so shear will be less. In this case, since the length reduces, so the shear becomes too large, right? So the horizontal force here is large, therefore you have this damage, right? So whenever you have this partial height walls, you have this short column effect. So how to handle them? So for them also people have come up with various techniques that they start modeling the hinge from this point to this point. So the people are there actually who want to do some research on anything and everything, but the best option here to avoid that kind of is to avoid the failure, is not to model the failure. Even if you model this using the strut, you're not avoiding the failure, right? You're just finding out how to model the behavior. Our job is to avoid it, to prevent it. So there are various techniques using which we can actually do this. So one technique, simple technique is you do not continue the opening till here. You have some infill wall. So the opening size will be somewhere here and don't have the entire length open. Right? So there are various techniques using which you can control this. And if at all it is not possible to do this, then of course you have to design these short columns for large increased shear force, right? Like this. Okay, so the final point about this modeling issues is the strength. How much is the infill strength and how to find it out? So, I mean, when you model it, uh, now we are actually slowly moving towards the non-linear analysis. Because in linear analysis, you never require the strength. Okay, because in linear means the you apply the load and the moment will keep on increasing, the displacement will keep on increasing always. So you don't need the strength, you don't need to tell the software that this is where you need to fail. It cannot be done in linear analysis, but in non-linear analysis, you can actually control the failure. You can tell the software that this is where the masonry should fail. Now that can be defined you by defining that the failure can be modeled by defining the material strength. You know how to define the concrete strength and the steel strength, but we'll again discuss those issues tomorrow in the nonlinear analysis presentation. But today I will only discuss the infill strength issues. So what do you need to define the strength of infill? If you're doing a nonlinear analysis, you not only require the single point, that is the strength, but you also require the entire stress strain curve. So here is a curve, the stress strain curve proposed by me back in 2007. So it shows you on the y-axis is the compressive stress, on the x-axis is the compressive strain. And this is the compressive stress and strain for the masonry prism, the 5-brick high masonry prism. Okay, so I tested hundreds of such masonry prisms. This is why during my PhD I carried out this work. So I tested hundreds of these masonry prisms along with the tests carried out on single brick units and mortar cubes. Then I came up with this equation. This is the equation using which you can compute with Fm or Fm prime, the prism strength of masonry under compression. What do you need to compute this? You need the brick strength, Fb, and you need the mortar strength, Fj. Now you may ask me, why do you need this equation? Because you can directly go to lab and test the prisms. Of course. So if you can test the prisms, then there is nothing better than that. But constructing prism and testing in lab is not easy. Right? It takes time. So 28 days of curing is required. Before that, you have to find someone who can do this testing. So what I propose there, that even if you're not capable or you don't have those capacity or the facilities to do the masonry prism test, you always know what is the average brick strength in the region. So FB you already know. And you also know with the experience like what is the mortar strength people generally use. Because mortar is defined by the ratio of the cement and sand. So 1 is to 6, 1 is to 4, 1 is to 3. There are not many there are not many types of mortar used in India. 1 is to 3, 1 is to 4, 1 is to 6, 1 is to 8. 4, 5 only across India. So we have some idea about the strength of mortar because many people have done tests at several locations. I mean, millions of tests. So that data is available. But considering that the brick strength varies across India, the strength on bricks we have to carry out. But still, we have some idea on strength of bricks across India. So if we know this FB and FJ, you don't have to go to lab and compute FM. So this simple formula here, it gives you FM. And this is a very interesting formula because the error is very less if you use this formula. Now, this is not sufficient. If I just give you FM or FM prime for the masonry, it is not sufficient because in nonlinear analysis, in addition to specifying this FM prime, you have to specify the entire curve. Now, entire curve means you have to specify the strains also. And now the problem will come. So, taking a prism, constructing a prism in lab and testing in compression testing machine, getting FM prime is still easier. But then getting the strain values and getting strain values after peak is more and more difficult. You cannot do it using the normal testing machines. You have to use the displacement control testing setup. So then I proposed another equation that will give you the strains also. So this epsilon m prime gives you strain corresponding to fm prime. So let us see this figure here. So what I proposed based on the test results, that this initial curve is this parabolic variation. From here to here is the parabolic variation given by this equation. After this parabolic variation, when it starts dropping, the failure is sudden. So we can have a straight line variation. So if you are adding line, then it goes slightly further in the strain axis. If you are not adding line, it will not go much, right? So this is Fm prime, this is the strength, this is the corresponding strain value. This is the point up to which the parabolic variation will be there. So it corresponds to 0.9 Fm prime. So we are considering 10% reduction in the strength. Up to that point, the parabolic variation is considered, and this is the strain value at that. Okay, and you can get that strain value from this equation. So that parabolic equation is defined here. Now, how will you get epsilon m prime? Epsilon m prime, this equation was proposed that depends on this fm prime and E, which again we know, and another parameter is Cj. So Cj can be obtained using this equation, which depends on Fj, that is the strength of the mortar. So if you use these equations along with this parabolic variation, you can plot the entire stress strain curve of masonry prism without even going to lab. Okay. So, and of course, the modulus of elasticity is 550 times Fm prime. That is also observed. That was also observed during the test. So this is how we define the infill strength. But if you're not interested in the entire stress strain curve, you just remember this equation that gives you the strength of masonry. So if someone tells you that I have this brick of which the compressive strength of this brick is 10 MPa and I am planning to use 1:6 mortar whose compressive strength is again 8 MPa or something like that, you can very easily find out what is Fm prime directly. So this is how we define the strength. Now, once we know how to define the stiffness and strength in our analytical or numerical model, we can do the analysis in the usual manner. Now, let us see what our code say, IS 1893-2016. So it says that First, very important point for buildings with infill walls, that if the story stiffness and strength variation along the height of the RC buildings with moment resisting frames and URM infill walls. See, this word URM is important here. That means unreinforced masonry, URM. So there is no reinforcement in these infill walls. That is important. So we consider it to be irregular. So there is a table given in the code, table 6. So we consider these frames to be irregular. If these are irregular, then we have to correct that irregularity. If the building is lying in seismic zones 3, 4 and 5, so Jabalpur is again spared. You people should feel happy. But in zones 3, 4 and 5, you have to correct that irregularity. So just go back and see what are these types of irregularity mentioned in table 6. And this is very interesting. You cannot design for these irregularities. It is very clear. It says that you correct the irregularity. Then the code says that you can consider the modulus of elasticity as 550 FM prime. So the estimation of in-plane stiffness and strength, this is useful. Then it gives a slightly different formula for computation of FM. I'm not sure from where this formula has come, but it is slightly different than what I proposed. Maybe it is taken from some other resources. So using these two equations, we can get, the second equation gives you the strength, first one will give you the stiffness. How about the area? So for area, the code gives us this equation for computation of the width of the strut. Now, this is a slightly complicated equation. It was proposed by Mainstone long back. So that equation is proposed here, and it is given by this equation, which is a function of alpha h. This is alpha h. So alpha h is actually the ratio of the stiffness of stiffness of the frame and stiffness of the infill. So it's a function of the relative strength and stiffness of infill and frame. Okay, basically the stiffness. And then the LDS. So LDS is the length of the diagonal strut, right? So this is same, but this factor is different in the code, right? So you have to compute these things. Here EM is the modulus of elasticity, T is the thickness of the wall, and theta is this angle. So angle that this diagonal strut makes with the horizontal. The role of this theta is actually to define how slender is the wall, how long is the wall. Because if the wall is very long, you will have theta less. But if the wall is very short, height is long, then the theta will be large. And EF is the modulus of elasticity of the frame. IC is the moment of inertia of the column section, and H is basically the height of the frame. So as I told you, it is a function of relative stiffness of the frame and the infill. This is slightly complicated, but we can find it out. And the code says that you model the infill wall using equivalent diagonal strut. If there is no opening, then of course the diagonal strut formula is that. But if there are openings, it says that you don't have to worry about the reduction. So it says it's okay if you have openings. So thickness of the equivalent diagonal strut is taken as the thickness of the original infill wall, provided this is satisfied. So the code does not allow the slender walls, very slender walls and very long walls. So h by t and l by t should be less than 12. Okay, so similar proposition is there in the code, right? So this is what the code says about the strength and stiffness. Now the question is, which of these two should be stronger? The frame should be stronger or the infill should be stronger? So we have seen, there are thousands of tests carried out considering different strength of infill, different types of infill, but this question will always be there. But then past earthquakes, they suggest that if the infill is very strong, and even if you design the RC frame nicely, still the stronger infill will inflict damage to the columns, like we have seen in the previous test results also. So because of the formation of the diagonal strut in the infill, now you can imagine if the infill is very strong, the uh, the diagonal force, the axial force in the infill will also be higher. And when this axial force is higher, the shear that is transferred to the column will also be higher. So the columns will fail. That is what is happened. That is what was happened in this building. The infill was so strong that because of that, the infill failed. Along with that, it forced the columns also to fail. So infill should always be weaker than the frame. That is what we have uh, found out. But there are some beneficial effects of the infill, and these are that we can increase the lateral strength of the frame, we can increase the stiffness, we can actually the overall ductility, if you look, is increased because of the formula of the ductility. The ductility is defined as the ultimate displacement divided by the yield displacement. And you can imagine that if the stiffness of these infill frames is very high, so the yield displacement is also very high, very less. So when the yield displacement is less, obviously the ductility will improve. But this is not the correct way of defining the ductility. And when we have additional material as infills in the frame, you will be very happy about high energy capacity of these frames. Right? When you have these masonry walls, they crack very easily and they keep on dissipating the energy. So the amount of energy dissipation in these infill frames is very high compared to the bare frame. So this figure shows the relative performance of the bare frame and the infill frame. So this is the bare frame without infill wall, and this is the infill frame. So the interesting point here is, although the initial stiffness of this infill frame is very high, the initial strength is very high compared to the bare frame, but then as soon as this infill fails, the strength and stiffness becomes very similar to the bare frame. So that is why we need to design this frame as if there is no infill, right? But then we have to consider the influence of infill on the RC members and improve their seismic design, especially the shear design. So these are the beneficial influence. If you have a bare frame, just look at the bending moments. If you apply this H lateral load, the bending moment in the beam and bending moment in the column is about 30%, 20% of H, right? But if you model the infill frame, it reduces drastically. So here it reduces to 0.032 only, right? So that is the advantage. You can reduce the bending moment in the columns and the beams, but then this reduction is only applicable up to this region, right? So if you have a small earthquake, let us say, for smaller earthquakes, there is nothing better than providing the infill walls because they will very easily resist that load. But for bigger earthquakes, which are not frequent by the way, as soon as the infill walls fail, the entire load is transferred to the bare frame. So that is very interesting interaction. So I'll come back to this table that I have already showed you yesterday. So these two columns are very important. It shows you the minimum design force that should be there for the frame and the infill. The meaning is, even if the infill is present in the frame, you have to design that frame for at least 25 to 50 to 65% of the lateral load, considering that there is no infill. Okay, so what these codes say that even if you have infill frame, then also you model first the frame as the bare frame, find out the design forces. So you come here, find out these design forces by modeling it as a bare frame, and then you model the infill frame, find out the design forces. So even though the moments here are very less, but then you have to at least design for 50 to 60% of this load, this bending moment. That is what some of these codes say. But some of the codes are very silent. They were very silent, but then now our code, it will actually be forcing the designers to design this RC frame for at least 50% of the design process. Okay, even if the infill walls are there. So you have to model the your structure twice. One without infill walls, and but considering the mass of infill walls, and one considering the stiffness and strength of the infill walls. Now, how to account for the additional shear force? Once you know what is the shear force, then we have to provide special confining shear reinforcement in that zone. So there is a code, that is Euro code. It says that whenever you have infill wall in a RC frame, the entire length of the columns should be provided with the spatial confining shear reinforcement. The current code, it says only in the plastic hinge zones we have to provide the spatial confining shear reinforcement. But if you have the uh, infill walls, some of these codes say that you provide that along the entire length. But the current code says if you have certain openings, so columns near the opening should be provided with confining shear reinforcement, so that to avoid that short column effect, so we increase the shear capacity. And we must be careful when deciding about the position of the opening. There should be proper connection between the RC frame and the infill walls. Now, this is a step ahead. The next step in the design. So let us say you are interested in doing the performance-based design of these infill frames. So for that purpose, you need what will be the permitted drift values for different performance limit states. For example, if I consider the limit states defined in the FEMA document of USA, it defines three performance limit states: the IO level, which is immediate occupancy, the LS level, which is life safety, and the CP level, which is collapse prevention. So we did not know that what should be the design drift values for these three different performance limit states. So using some test results, my students actually developed this idealized lateral load drift relationship, and he suggested some design drift values for different performance limit states. For example, there are two cases here. One is for infill frames with openings and another for fully infill frames. So this dotted line is for fully infill frames. So these points here, they represent, and you can see different colors also. So these green points, they represent the cracks in the infill. Wherever they are, then the triangles, the red triangles, they represent shear crack in the column. So you can see here where the shear cracks are forming, at what drift levels the shear cracks are forming in this zone. And then these are the peak lateral load points that are defined. And this plus represent the 80% reduction in the peak lateral load. So these happen at these drift levels. So these are the drift levels corresponding to different damage states in the infill wall, in the infill frame, right? First damage state is cracks in the infill, which happens up to about this green box. Second damage state is the shear crack in the column. So it is defined by this red box here. Third damage state is flexural crack in the column, defined by this blue box here and the blue points, of course. Fourth is the peak, the strength values, and the fifth is this reduction in the strength. So depending on these, he defined the design drift values for these three performance criteria. So these are the values. So about 0.45%, about 0.9%, and this is about 3.4%. Okay, so this is what is required in the performance-based design of the structures. That can be followed later. So that is all from me. Thank you very much. This is our academic complex building in IIT Guwahati. So if we have the reason of showing this is these are all infill frames. So if we have any questions, we can discuss.
Thank you very much, sir, for this session. Now I request all the participants to ask their questions.
Sir,
Yes.
sir, in India, my name is Nilanjan Samanta. In India, mostly infill walls are non-integral types. So for non-integral types, infill wall many times out of plane failure occurs. So in that case, what is your view? that do we need to consider its stiffness, or we should neglect its stiffness because this is non-integral nature.
See, what is engineered infill?
So, in case of engineered infill, generally integral infills are used, reinforcement bars are used, and those are connected with beams.
So we are not discussing about those infill walls. If somehow you have connected the infill with the frame, that takes care of the out of plane effect, right?
Okay.
And we have already discussed that we are not discussing the out of plane design or out of plane safety here. I am assuming that somehow by providing certain restraints, by providing certain angles or flats or FRP, we have actually prevented the out of plane failure. If we are successful in doing that, then how to design the infill wall or the infill frame or the in-plane forces. That is what we have discussed today. Now it has nothing to do with the engineered infill or the non-engineered infill. I am assuming that out of plane failure is avoided.
Okay. Okay.
Okay. So even if in that case, even if the infill is very weak, then also you have to design it. You have to consider its influence.
Okay.
Because weaker infill means, let us say, you have 5 MPa brick and you have 10 MPa mortar. So a combination of that will give you about 3 MPa of masonry prism. Now this 3 MPa is also some significant number when you apply the diagonal compression on this.
Yes.
So it will also enhance the stiffness and strength of the frame. Okay.
Okay.
Sir, I just wanted to ask out of curiosity, just like while constructing this column like frame during construction, if we do that, we project bars from the column in between the columns in horizontal direction, and
Yes.
then we provide that infill. So will it provide the means sufficient lateral strength or something like that? Like you have said that along the column in X shape, you provide that bands and plastic
Yes.
it. Will
Yes.
it be also be possible if we provide the horizontal bars from the columns and it will be connected to the column?
Yes. See, our ultimate goal is actually to divide this long wall or high wall into
Yes,
smaller segments.
yes,
Right? So the problem with the long wall or the high wall is that it will vibrate because of the length, it will bend and it will fall.
yes,
But somehow if you can reduce that free length of the wall by providing intermediate members, then of course you can improve the out of plane nature of these infill frames.
yes,
And one method is actually by providing the sill level band
yeah,
right along the whole length of the wall, then by
yes,
providing lintel level band along the whole length. That
yes,
is still possible. But one important point that we must remember, if you remember that presentation in which I showed that the member was later connected to the RC column, one
yeah,
member, by removing the concrete and exposing the bar.
yeah, yeah, yes, sir.
We should
Understood.
not do that.
Yes, yes, yes,
That should
yes,
not be done. So we should plan it properly and we should lay the steel bars during
yeah,
construction of the columns. We should leave some bars at some locations for
yes.
providing bands.
Okay, sir. Okay.
Another important point is this sill level band or lintel level band should not be very big size. So they should be
Yeah.
very flexible.
Yes. Yes.
In the sense, their job is only to reduce the effective free length of the wall.
Yes.
If we provide big size sections, then what happens? It will actually interact with the column,
Yeah.
and again the force will be transferred to the column. That we don't want.
Hmm. Okay, sir. Sir, one more thing that you have given that expression for masonry, compressive strength of masonry, I think.
Yes,
Yeah, FM prime. So
yes.
for that means during testing, you have considered bricks from all over India or some specific region? Like,
No, yeah. In that study, we considered bricks from UP.
yes, sir.
Okay, But here, when I joined Guwahati, we have done another study in which we considered bricks from Assam.
Yeah.
And we also did study in which the different types of bricks were considered, for example, the fly ash bricks.
Yes, sir.
And then there are many more studies which are carried out across the world. Those are actually trying to develop the stress strain curves for different types of masonry.
Yeah, yeah.
But what we have seen that the expression that I showed here
Yes, sir.
is very well applicable to the masonry across the country if
Yes.
its strength lies between 5 to 25 MPa.
Okay, okay,
Okay.
okay. Okay, so participants, if any more question you wish to ask, you may ask.
Sir, I would like to ask you
Yes.
that you have shown today that there is large variation of strength between northern bricks and southern bricks. So
Yes.
I would like to know that what is the differences in weight, or I mean density, between northern and southern, because that will causes lesser weight on building. So is there any drastic variation of weight, or only strength, the drastic variation in strength?
So what I showed here is only for clay bricks.
Okay.
Okay, this variation in strength is only for clay bricks. And I think there will not be much difference in the density of the clay bricks across India. There may be
Oh,
small difference, maybe 5-10% variation, but not much. Because the manufacturing process is more or less similar for these clay bricks.
yes.
But yes, nowadays many different types of bricks are coming. For example, the lightweight bricks are there, which are not solid, right? So of course the density will be different. Then you have fly ash bricks, of course, that we are testing. Then many different sizes, big blocks are coming up now, which are lightweight. So we need to do tests on different types of bricks. We have not done tests yet.
Okay, sir. So I think there is
Hello,
no
sir.
more
I have
questions
one
there.
question.
Yeah, yeah. Okay, okay.
Yes, sir. My name,
You can
yes, sir.
ask.
My name is Ravi, sir. Sir, I have a question related to response spectrum, which I couldn't ask yesterday. Sir, I am doing some response spectrum for RC frame with shear wall. So, sir, I need to assign a response spectrum function. So, in this, sir, which type of response spectrum we means? If we use design spectrum or other code spectrum or other previous earthquake occur like El Centro earthquake.
See, it depends on what type of analysis you want to do. Let us say I want
So I
to
am doing
carry
some
out,
response.
yeah, let us say I want to carry out an analysis considering different ground motions, developing their response spectrum, and then see how the structure behaves. That is one way of doing that. Another way is I will do that. That I will carry out analysis for only Indian response spectrum. That is another way. So it depends
Okay,
on
sir.
what you want to do actually. It's not there is. I mean, if you want to
Okay,
design
sir.
and the structure is to be designed in India, then of course you have to use IS 2890 design response spectrum. But if you want to check your
Okay, okay.
structure and compare the performance, considering the response spectrum of different countries or different maybe different ground motions, then you can do that.
Okay, okay, sir. Thank you, sir.
Good afternoon, sir.
Good afternoon.
Sir, I have one doubt that while we scaling the time history with respect to response spectrum, so we have to scale it with elastic response spectrum or inelastic
So scaling of
time history.
scaling
Time
of.
history, sir.
Scaling of time history.
Okay, okay. So see, I mean, I am assuming that you're scaling the time history to achieve your design response spectrum. Am I right?
Yes, yes.
So then that response spectrum you have to consider.
Sir, but in the magic equation, the value of R we assume is 5. That means we have considered ductility in the structure.
No, 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 no. See, these are two different issues. See, if you want to carry out, let us say, dynamic time history analysis for a structure for any given ground motion, that is free. You don't have to worry about what is R value, what is not, because that's a different issue. Okay. But then the question will be asked, like, why you chose this ground motion, right? So then what people do, they modify the ground motion. So they simulate the ground motion such that it becomes equivalent ground motion, which gives you the design spectrum, right? But this ground motion may not be the actual ground motion. Then you'll be surprised to see the shape of the ground motion will be completely different. It may not look like a ground motion. So that is another way of doing that. That you change the ground motion so that it reflects or it looks like the response spectrum of that ground motion looks like the design response spectrum. Now the question will be, what will be the values of this acceleration, right? So now you have to use all those multiplying factors in order with the SA by G to get those values. So an R is also a function of that, right? So depending on your structure, then you have to multiply all those values. But it is, I mean, this is one way of doing it. Another way, a better way that people say that you consider a combination of, let us say, 7 ground motions or 9 ground motions or 15 ground motions. You consider ground motions such that they have different magnitudes, they were recorded on different locations on different soil types, in the sense that when the waves travel from focus to this station, the waves travel through different soil profile, different duration earthquakes, then different frequency earthquakes. So if you have 10 to 12 different types of earthquakes, and then you do the analysis, that will suffice.
Okay. Thank you, sir.
Okay, sir. Thank you very much for this wonderful session. I hope there is no more
Okay.
questions. So, thank you, sir. We can end now meeting and
Okay.
see you in the next meeting. Yes, sir.
Yeah. Okay.
Yeah.
Thank you,
Okay.
sir.
Thank you.